triple integrals using spherical coordinates. Now in this section, it is very similar to that of cylindrical coordinates in that we are just basically going to use a different coordinate system to solve triple integrals. Now once again, many times converting from rectangular to cylindrical or rectangular to spherical will offer a more convenient computation of the triple integrals. However, it won't always guarantee a more simpler computation. Sometimes it actually does make things simpler. Other times it makes it more difficult. Really, it's going to be your decision when you take an exam on which coordinate system you should be using, rectangular, cylindrical, or spherical. And really by practicing and just knowing the signs and seeing things that are kind of obvious are going to help. So now let's move on into the new coordinate system that is spherical coordinates. Now when integrating triple integrals involving spheres or cones, it is often wise, notice it says often wise, not always wise, but it's often wise to evaluate by converting to spherical. Now, if you'll notice that we have a point here, P, X, Y, Z. So like that's typical coordinates for rectangular. Well, we could also describe these coordinates as spherical using these three letters here, or variables I should say, rho, theta, and phi. So this point here, P, can be described either with X, Y, Z, rho, theta, or phi, but it also can be described with cylindrical coordinates as well. In this section, obviously, we'll be talking about rho, theta, phi. All right. First, I want to point out, how do we get that letter rho there, the first coordinate rho? As you can see, it's being kind of it's highlighted there. Rho is literally the distance from the origin physically to the actual point P. So you draw a line physically from the origin to the point P. That will give you your first coordinate rho. But that would be kind of tough to do because really you can go anywhere when it comes to rho. How can I constrict that down to a specific location? Well, you need theta and phi for that. Next up would be theta. And actually theta is similar to, or the same I should say, as the theta you find in cylindrical coordinates. And theta is essentially the angle on the floor where z equals 0 that forms an angle with the positive x-axis and also with the line that is being projected down from the point itself. So again, notice that this line rho here is being projected down onto the floor right here. Okay, so the angle that it's creating here is going to give us our theta. Okay, and finally phi. What is phi all about? Well, phi is actually the angle between the positive z-axis and the line segment OP. So this line segment OP here, whatever angle it creates with the positive z-axis will give us our angle phi. Right there. And just like rectangular coordinates, just like cylindrical coordinates, these coordinates all can also describe the same exact location of P in any direction. A couple very important facts, though. One fact that you'll need to know is, first of all, rho must be positive. It must be greater than or equal to 0. It's not like r in polar coordinates or cylindrical coordinates where r could be negative. Rho must be positive at all times. That's the first fact. Second fact I want to point out is that phi must be between 0 and pi. Phi must be between 0 and pi. And the reason for that is that between 0 and pi causes me to create points that are from 0 to pi over 2, gives me points from the top half of the hemisphere when it comes to spherical coordinates. And pi over 2 to pi gives us the lower half of the sphere in the spherical coordinates. But these are very important facts that we must kind of keep an eye on when dealing with spherical coordinates. You cannot violate these facts. One other good thing about spherical coordinates, and please do not shy away from it. I know some of you guys just learned about cylindrical and you're probably pretty good at it by now. But spherical coordinates utilize very much a symmetry in the origin. So, if you have a situation where symmetry is apparent, and the origin is obviously in a very convenient location with respect to your solid of integration, then spherical coordinates is a possible good choice for integrating a triple integral. Now, a couple of generalizations of what I'm talking about here. If you take a look at this page here from the book, here's a couple examples of what spherical coordinates, how they can be described using spherical coordinates. For example, if we take a look at this, theta equals some constant c. Well, theta equals a constant c is going to be known as a half plane because, once again, don't forget, the angle for phi must be 0 to pi over 2. So it must follow along this plane. Okay, it has to follow along this plane, and it can't go back around here. Okay, all right, it can't do that. So this can't happen. Okay, it must stay in front of the angle here. All right, but also, as we'll see later, I'm going to explain in a moment, what if we have phi is equal to a constant? Well, phi equaling a constant is actually going to lead us to either an upper half cone or a lower half cone. So it'll be an upper half cone if the angle is from 0 to 2 pi, or pi over 2, excuse me. It'll be a lower half cone if the angle is from pi over 2 to pi. And the reason why it's a cone is because, as I'll explain later, it's being spun around by the theta. The theta has not been restricted here. So this is being spun around, and obviously rho can be any point away from the origin, so it can be all the way as close as the origin itself. And again, this cone does not stop here at this circle on the end here. This cone goes on forever. So rho can be any length at all. So let's go ahead and take that previous sketch again, and let's go ahead and add some elements to it. Notice here, if you compare this sketch to the previous sketch, here I went ahead and pointed out the distance x. That's the distance from the origin out to this dotted line here. Sorry, it's kind of hard to see. This distance y is going to be the distance from here to here, parallel to the y-axis. And then obviously the z distance here is going to be my distance from the origin to Q. Okay, so I just kind of added that to the mix, but all that's describing is what's going on with the rectangular coordinates here. So again, the x, y, z that you see on the axes are just going to represent how I even got to this point P to begin with. But then, of course, we want to convert this to spherical coordinates. Now, by doing this, we have created a few objects in the picture that you'll hopefully agree with in a moment. But first, what I want you to notice is how I have these dotted lines up here and this dotted line down here. And notice how these dotted lines created several right triangles. And of course, we have this right triangle from the original picture in the middle. So as far as I can see, I see 3 right triangles in the picture here. And based off of our experience with trigonometry, basic trigonometry, I should say, I would think that these 2 triangles, so OPQ and OPP prime, create the following relationships, and I hope you would agree. So would you agree that, according to this picture, that Z is equal to rho cosine phi? And if you agree, and you can already see it, then great. But if not, let me go ahead and just give you a little more closer look at what I'm talking about here. So I'm looking mostly at this triangle here. So the triangle that goes from here to here, here to here, and Q back down to the origin. Okay, so this triangle here that I'm highlighting. Well, if you're not convinced that that triangle gives me this relationship here, So to convince you, I'm going to go ahead and redraw this highlighted triangle right here. And I think we all can agree that this triangle accurately depicts the highlighted triangle here. Notice that you have your angle phi right here. And that in this picture, I know it looks a little bit skewed, but notice how in this case the rho is across or opposite from the right angle. So that makes it the hypotenuse, obviously. And then the adjacent side here is going to be z, so that obviously makes this adjacent side here z. So having said that, I think it's pretty easy to see that this relationship is true because obviously since z is the adjacent side and rho is the hypotenuse, well then obviously the relationship here of cosine of phi is going to equal to adjacent, which is z, over hypotenuse, which is rho. And so seeing the picture here, I don't think we all are too perplexed by this now. And simply all I do is just multiply both sides by rho, and that will give me this relationship here. So now that you can see this clearly with all the trigonometry in front of you, that relationship should make sense to you now. Okay. On a similar note, if you look at the other triangle here, in fact, if you take a look at this triangle, I'll go ahead and highlight using a highlighter again. So this other triangle, it's kind of over here. So this guy, again, with rho being the hypotenuse here. This other triangle over here highlights the fact if I use alternate interior angles, so meaning if I take phi and I notice that it's the same exact angle as this guy, well, this second triangle over here shows us a relationship of opposite over hypotenuse, which would be sine. So this other relationship here also should make sense to us. And you might be wondering, well, okay, so what? The question really is not so much so what, but as so what now? Well, the what now is that we now have established some relationships here. We now can see how z is related to rho and phi, and we can see also how r is related to rho and phi. Having said that, let's go ahead and take a look at our relationships here. Now, we already know this from cylindrical coordinates. Now, we already know from cylindrical coordinates that x equals to r cosine theta. We also know that y, according to cylindrical coordinates, is also equal to r sine theta. Well, simply all you have to do is take these cylindrical coordinates and literally replace the relationship that I had before from the previous page. Notice in the previous page, we actually did have the relationship r, didn't we? That relationship r got substituted for the previous relationship from the previous slide, which is rho sine of phi. Same thing here. This relationship of r, it got replaced by rho sine phi also. Just notice that the cosine theta just simply came down, as did the sine theta here. So that gives us our x coordinate, that gives us our y coordinate, and it relates those coordinates to not just rho and phi, but also rho, phi, and theta. And then, of course, z was already established from the previous page based off the triangle that I showed you. And therefore, we now have our relationship here that translates or converts our rectangular coordinates of x, y, and z to our spherical coordinates of rho, phi, theta. So now, if we are trying to convert from spherical to rectangular, these are the formulas that we're going to use right here. Okay. Moving on. What if I want to convert from rectangular back to spherical? Well, spherical coordinates are typically based off the distance from the origin to the point itself, which is rho. If you actually think about it, rho, if you actually were to take the same distance rho and move it anywhere you want in the three-dimensional space, you actually would end up with a sphere. This is actually an equation of a sphere. More specifically, we actually get what's known as a spherical block, because obviously we're not going to be dealing with a sphere, a whole sphere, typically. Typically, we'll be dealing with a part of a sphere, or what's known as a spherical block, or sometimes even a conical block, which I'll show in a minute. Where again, rho must be positive. It has to be greater than or equal to 0. So that means rho 1 must be greater than or equal to 0. Theta at most could be a distance or an interval of 2 pi. And again, make sure that phi is always going to be between 0 and pi, which means phi 1 and phi 2 must also be between 0 and pi. So here we're going to go ahead and change from spherical to rectangular. So since it's spherical, that means the given coordinates here are spherical coordinates. And we're going to change these into rectangular. And having said that, please remember, spherical coordinates means the first coordinate is rho, the second coordinate is our theta, and the third coordinate is phi. Let's remind ourselves what those formulas look like. So here's my formula for x. X is going to equal to rho sine phi cosine theta. Y is rho sine phi sine theta. Z is simply rho cosine phi. And all you simply do is plug in the values and you're done. So it's pretty simple. I don't see how really anyone would struggle with this particular problem. So for example, if I plug in my values for phi, rho, phi, and theta, you'll notice I get cosine pi over 2 in there, so that becomes 0. My values for my value for y, I plug those in. Sine of pi over 2 is 1, so I go ahead and find sine of 3 pi over 4, which is rad 2 over 2. And then the 2's cancel, leaving me with just simply rad 2. And finally, z, and just plug in those values here, and you end up getting negative rad 2. Thus, our rectangular coordinates are 0, rad 2, negative rad 2. So again, I don't think these are too tough. So let me just do one more very quickly. So again, following the formulas, you just simply plug in your rho, your theta, your phi. You get 1, y is 1 in this case, z is rad 2, again giving me my rectangular coordinates, in this case 1, 1, rad 2. So now let's go the other direction. Let's change from rectangular to spherical coordinates. Now in this particular problem, you might notice that the question given, the point given is familiar because it's the answer to the previous slide, obviously. So I think we can predict when converting back to spherical, we can probably predict what the answer is going to be. And the best way to do this, though, is to actually follow the relationships that were given to you from previous slides. And I would say the best process would be to determine which relationships help you determine these spherical coordinates. And don't forget, the spherical coordinates are rho, theta, phi. Now, me personally, I like to start with rho. So the relationship I would like to use in order to determine rho is this one right here. So this is the first relationship I would recommend you use. Rho squared equals x squared plus y squared plus z squared. And the reason why is because you'll notice that again we are given our rectangular coordinates. And so this first coordinate is x, second is y, third is z. And all we simply do is plug them in here, take the square root on both sides. Now obviously when you take the square root on both sides, you tend to get a plus or minus situation. However, don't forget that rho must be positive at all times. Therefore, we are only going to consider the positive case. So again, a very easy formula for us to follow. We have now just found our value for rho in a fairly easy way. Once you have rho established, I would also like to point out the next relationship that I believe will help you in determining the next portion of your spherical coordinates. And for me, the next coordinate you should look for is phi. And the reason why is that you have this relationship here. And this relationship would be rho times cosine of phi. And the reason why this is a good relationship to use at this point in the problem is because we already have, yes, we have 3 variables here, but 2 of these variables we already know in the relationship. We already know that z is rad 2, so that's going to go right here. Okay, and we already discovered our rho is 2, so that's obviously going to go here. So having said that, we go ahead and divide both sides by rho. We end up getting cosine phi equals rad 2 over 2. Again, the top here is our z value. The bottom value here is rho. And obviously rad 2 over 2 is a very common ratio that you've seen many times in trigonometry and pre-calculus and beyond. So obviously cosine of phi is equal to rad 2 over 2 is going to give us a degree of phi equals pi over 4. So we found rho, we found phi, now time to find theta. So all we have to do is find a relationship that includes theta in it, and obviously x and y we saw from previous slides, x and y have been defined as spherical coordinates in terms of rho, phi, and theta. So we can use either x or y, it doesn't matter. I'm going to go ahead and use x. And as we can see, we have rho, phi, and theta involved. And from previous steps in this problem, we already found out what rho is. Rho is 2. Phi, we already found out, is pi over 4. And x was given from the very beginning of the problem, which is 1. So we simply plug in those values. And in this particular case, not only plug in those values, go ahead and solve for cosine of theta. And that's going to give us this situation here where we actually have cosine of theta equals to 1, that's the x value, divided by 2, that's the rho value, sine of pi over 4. We all know sine of pi over 4 is rad 2 over 2. The 2's cancel, you end up with 1 over rad 2. Once again, 1 over rad 2 is a very common ratio. In fact, this actually, once you rationalize it, goes back to rad 2 over 2, which gives us, again, pi over 4. And as predicted, our spherical coordinates are 2, pi over 4, as you already probably guessed. Let's try another one. So it's obviously going to follow the same protocol or very similar. There's some slight twists to this one that you might find interesting. Let's start with the easy one again, the relationship of rho to x, y, and z. It's going to be the same thing as the last slide, so I'll just get right to it. Rho in this case is going to ultimately end up equaling 4. So that one's not too difficult to understand, I hope. However, phi, a little bit of a twist to it. Not much, but a little bit. So in this particular case, don't forget that phi has the relationship of cosine of phi is equal to z over rho. So obviously that relationship is going to give us negative 2 over 4, which reduces to 1/2 or negative 1/2. And that's going to give us phi is equal to 2 pi over 3. Now, a little basic trigonometry knowledge tells you that, well, cosine of phi equaling to negative 1/2 has infinitely many different answers. So how did I know to pick 2 pi over 3? Well, it's because it's a very simple fact. Don't forget that phi must be between 0 and pi. So where is cosine of phi equal to negative 1/2? Well, that's going to be obviously past pi over 2, but not past pi. So the next point where cosine is going to be negative is going to be at, in this case, 4 pi over 3, which obviously would be outside the bounds of our requirement here. So please don't forget this fact. That way you'll know that phi is definitely going to be 2 pi over 3. Finally, we move on to theta. So obviously theta, from the previous slide, is going to be found by utilizing the you can use y, you can use x, you can use either one. Here obviously I went ahead and used x. Don't forget it's going to be x over rho sine phi is the relationship here. Simply plug in these values. Obviously rad 3 stays up here over 4, and sine of 2 pi over 3 is rad 3 over 2, so the rad 3 over 2 goes down here, but that 2 obviously flips up to the top. Do some simple algebraic manipulation. We end up with negative 1/2 here as well. And so basically our answer here is going to be either so which one is it? Well, keep in mind that there are some restrictions, and always, as you have done before in previous conversion problems, keep your eye on the original problem. So for example, in this particular case, theta in this particular case is actually going to be 4 pi over 3. And the reason why it's 4 pi over 3 is because notice that in this case y equals negative 3. And since y equals negative 3, if you go back to your old polar coordinate knowledge, if y equals negative 3 and x is negative radical 3, that's going to land us in the third quadrant. And obviously 4 pi over 3 also lands us in the third quadrant. Please don't forget that theta is going to be on the xy plane. Just like in polar coordinates, it's the same in spherical coordinates. Theta will be on the xy plane, and obviously a point of negative will lead you into the third quadrant, which means you choose 4 pi over 3. Therefore, our answer in this case will be and these would be our spherical coordinates. Now earlier I mentioned briefly about how we can describe certain surfaces, and now this particular surface says phi equals 2 pi over 4. Now recall earlier that when you have simply phi equals pi over 4 and there's no other restriction on the surface, in fact you'll notice here that rho and theta are absent. That means rho and theta can be whatever we want it to be. And so I briefly described what that actually becomes. You saw earlier in the lesson that that actually becomes a cone. So again, notice that there is no restriction on rho or theta. So essentially, we end up getting a cone, and I'm going to go ahead and describe essentially what that means. So what we're going to actually get is the top half of a right circular cone of angle pi over 4 with vertex at the origin and a positive z-axis. So if you'll notice that in this particular case, this angle here is an angle of pi over 4. And because rho and theta have no restriction, what that means is that, let's start with theta. Theta is pretty easy because what you do is you take, let's just take this edge for example. If you can kind of see this edge, I'll kind of highlight it a little bit. If you take this edge, and by the way, this edge goes on forever. Now that's where when I start talking about rho. But if you take this edge, which goes on forever, and you essentially spin it around the positive z-axis, 360 degrees, that's going to give us our limitless theta. Theta can be from 0 to 2 pi. All angles of theta are achieved between 0 to 2 pi. Those are unrestricted. And on top of that, theta is also unrestricted. Remember, this little circle up here that seems to cap off the cone actually goes on forever. And let's recall that what's rho? Rho is the distance from the origin to the point itself. So basically any point on this cone at all fulfills this restriction of phi equals 2 pi over 4. But again, this cone does go on forever, but obviously we wouldn't be able to draw that. We just draw it and cap it off somewhere for to simplify our lives a little bit. But abstractly, this thing does go on forever and represents a cone. In fact, specifically a top half of a right circular cone. If I wanted to represent the bottom half, let's say I wanted the same exact cone but flip it exactly upside down, then I would have to actually take this angle pi over 4 and subtract it from pi itself. And that would give me the bottom half. Now, let's go ahead and do some more converting now that we have a pretty good idea of what it means to be spherical coordinates and what, a little quick description of a specific surface. Let's get down to what we're really talking about here. What we're really talking about in this section is not only converting to spherical, but converting to spherical in such a way that you'll be able to evaluate integrals using spherical coordinates. And again, many times when you convert to spherical coordinates, if it's possible, you end up with a much easier integration computation. So for example, in this case, let's go ahead and convert this thing to spherical coordinates. Now you'll notice here, this right here, this expression, x squared plus y squared minus z squared, looks kind of familiar, but it's kind of unfortunate because if I simply were to change that minus sign to a plus sign, then we'd have that relationship of rho squared. This would become rho squared. I think we all would be in agreement with that. So you'd be like, okay, well, that's great, but that's not what you gave me. You didn't give me x squared plus y squared equals z squared. If I did, you would call this rho squared equals 16, and you'd be done with this problem. But that's not what it says. What this says here is x squared plus y squared minus z squared equals 16. So what we do to kind of help us out is we go ahead and try to do some sort of algebraic manipulation to try to force this thing to have rho squared in it somewhere. So I think we all can agree with this statement. Now, right now, you might not know why I'm doing this step here, but your job right now is not to understand why I'm doing this. Just, do you agree with this statement? Everyone within earshot of me right now, I think we all could agree that this expression here equals to this expression here. These two equal to each other, because obviously if I went ahead and combine these like terms at the end, these would combine to become negative z squared. I think we all could agree. And so you're thinking to yourself, so what? Well, the so what is this. On the right hand side, now that I've manipulated this thing, you'll notice that I manipulated it so that way in my expression, even though these are equal, and you're like, well, where am I going to go with this? Now, even though they're equal, you'll notice that this first portion of it is, in fact, my rho squared. So I ended up getting a rho squared out of it. So what I'm going to do is convert this to spherical coordinates. Is I'm going to replace all this here with rho squared. And of course, we already know what our relationship is for z. We have a formula for that. And this ends up becoming rho squared minus 2 rho squared cosine phi squared. So let me go ahead and point out where all that came from. So again, this rho squared here came from the first three terms here. And then z squared here ends up being this portion of the expression down here. And that's it. That's all you have to do. And you might wonder, okay, what's the point of that? Well, the point is this. The point is that many times you'll find when evaluating triple integrals, you'll need to convert to spherical to get something that is actually going to give you a much easier integration process. And I have to warn you though, sometimes when you convert it from rectangular to spherical, it seems more complicated at first, but in actuality, it's much simpler. Now, you can also simplify this a little further. You could maybe factor out a rho square and you end up with this. Sometimes this is a better situation. It really depends on whatever suits your needs at the time. And you're just going to have to kind of work on these problems over and over again until you get good at knowing which version is best for you, this first one or the second one. I'll give you another example to kind of help you understand. So for example, with this one, we're going to write this one in spherical coordinates. And for this particular problem, there's actually 3 possible conversions. And once again, it's going to be your job to choose which one will suit your needs for that particular problem. Now in this particular case, it's kind of unfortunate because here I don't have a z squared here. So I don't have an x squared plus y squared plus z squared. Now if you want to, you can go ahead and add z squared on both sides. But I would say that's actually more complicated than you need to make it. What I would say is just go ahead and replace x squared with the relationship that we know to be x. X, we all know, is equal to rho sine phi cosine theta. And we all know that y is equal to rho sine phi sine theta. And if you simply replace the x and y with those 2 values, and of course we know what z is, we end up with this. Or once again, x squared leads me to this first term here. Y squared leads me to the second term here. And of course, the famous z relationship is down here on the end. Now, you could stop here. If I ever ask you to convert to spherical, we're done. This problem is complete. However, it will be a good idea for you to learn how to simplify this algebraically because this might be a great way to solve a triple integral, but you might need to simplify this a little bit more to make your life even a little bit easier. So for example, I could go ahead and simplify this further. You might wonder, well, how the heck did it come to that? Well, let's focus on the easy part first. First of all, notice that the right-hand side is the same as the right-hand side here, so that's not a problem. So how did I get this big old complicated expression over on the left, and how did it become this nice expression down here on the left? Well, if you take a look, technically I have 2 terms here. I have 1 term here, and I have 1 term here. You'll notice, what do they have in common? Well, they have rho squared sine phi squared. They have that in common in both of these terms up top. And if I factor those out, I end up with cosine squared theta plus sine squared theta, which you all know to be 1. And that's how this was reduced down to rho squared sine squared phi. And then finally, notice that both sides have a factor of rho. So you actually could go ahead and divide both sides by rho, give me a final answer of rho sine squared phi equals 2 cosine phi. And now again, these are 3 possible conversions. Typically, you're going to want to simplify this as much as you can algebraically, because once you simplify it down to here, you end up getting something that's quite nice and can be used easily in a triple integral situation. But believe it or not, occasionally just plugging in x, y, and z and leaving it as is the best case scenario. Typically, no, though. Typically, you are going to want to simplify these. So speaking of which, now that we have a couple of those under our belts, let's go ahead and talk about actually evaluating triple integrals. So in order to evaluate triple integrals, we want to go ahead and consider a few things first. Now, one thing I want to talk about is that, and I'll show you a picture in a moment, is that much like what we had in the past, where, like, for example, in previous sections we've talked about like a solid of integration. Well, our particular solid of integration in a spherical coordinate system is typically known as a spherical wedge. And essentially, a spherical wedge is going to have these limits here. And it's essentially the equivalent to the Riemann sum of a rectangular box in a rectangular coordinate system. It's known as a spherical wedge. And this is basically what it looks like. So imagine you're kind of like cutting off a piece of the sphere to get this. And if this looks really complicated and crazy, it's not something you're really going to be dealing with much, but it is a good thing to kind of look at. But if you kind of take a close look at this, you'll notice that this does indeed follow some sort of pattern where rho is between A and B. That is, rho is between this side of the sphere up to this side of the sphere. Theta is between alpha and beta, which means if you look at the floor here, you're going from an angle of alpha to angle of beta. And then again, obviously, phi is an angle from C to D, which gives you an angle from C on this side to D on this side. So if you're really on close inspection, you can see how this makes sense. But even if you can't, I'm not too concerned about it. But there are some facts you should know about spherical wedges. Again, this is a Riemann sum apparatus. Keep in mind that A must be greater than or equal to 0 because rho must be greater than or equal to 0. The interval from alpha to beta must be less than or equal to 2 pi. That way theta can go all the way around if possible. And also, don't forget, the difference between C and D must be less than pi, because once again, phi must be less than pi. And what this leads us to, it leads us to a triple integral. The triple integral, again, is going to begin with rectangular coordinates. And this is hopefully familiar for you. You hopefully have seen this before. I'm sure you have. And what it basically does, it leads us to triple integration of spherical coordinates. Now I'm going to go ahead and just let this sit for a second. In fact, I'd recommend you pause the video here and just kind of take a look at this, take it all in, and maybe even toggle back and forth between the last slide and this slide, and see if you can kind of make sense of this. So once again, the spherical wedge here, the same thing from the previous slide. So rho is between A and B, theta is between alpha and beta, phi is between C and D. And you might look at this and think to yourself, well, wait a minute, this is even more complicated. This looks crazier than rectangular coordinates. And I'm here to say that many times when you convert from rectangular to spherical, you actually get a much simpler integration. Now, there's a few things I want to point out. Now, there's the obvious. This here looks familiar, I hope. This is actually going to be x, obviously. You're going to replace any x you see with this expression. This here, obviously, is our y coordinate. You're going to replace any y coordinate you see with that expression. And finally, this coordinate on the end is obviously our z coordinate. You'll replace any z coordinate with that expression there. So far, I already have my x and my y and my z accounted for. Well, how about dv? We've dealt with dv in the past. If you recall, in cylindrical coordinates, dv ultimately ends up becoming r dr d theta dz. Well, in this particular case, take a look at this down here. This entire expression, all of it, the rho square, the sine phi, the d rho, d theta, d phi, all of that there is in fact going to be my dv differential. You must replace dv with that entire expression every time. So whenever you're going from rectangular to spherical, replace dv with all of that. You cannot miss one little thing from that expression. And to further illustrate this, please write this down if you're following along in the student notes. You must be sure to use appropriate limits of integration, and especially be sure to replace dv with rho square, sine phi, d rho, d theta, d phi. Now in this particular case, this is when your spherical coordinates are nice. If you'll notice, every single one of these coordinates here are all in between constants. That will not always be the case. In fact, as I'll show you later, the book shows you that there are cases where maybe the angles are all between constants, but rho, your distance from the origin to the surface or the solid itself, is not constant. Notice here that theta is constant, phi is constant, but rho is defined by a lower function in terms of theta and phi up to an upper function in terms of theta and phi. That can happen, and be ready. But once again, this seemingly more complicated triple integral many times ends up becoming a much simpler computation. So why don't we go ahead and do a problem that is already set up for you. In fact, the integration is no problem. The integration for this next problem, you could probably do right away. In fact, let's take a look at this one here. I guarantee that if I were to present this to you in the 2 sections ago, before even cylindrical coordinates, you would have been able to integrate this thing no problem. But since we're learning about spherical coordinates, it is important for us to understand what our solid of integration looks like. So what you do, and as you've seen before, we did this in previous sections, your solid of integration is always going to be determined by your limits. So these limits of integration will always determine your region of integration. So take a close look at your region of integration here. So hopefully you would agree with this following statement. Based on these 3 integrals here, and don't forget, the innermost differential corresponds to the innermost integral, the middle differential corresponds to the middle integral, and the outermost differential corresponds to the outermost integral. And based on that, I think you all could agree that my region of integration has rho between 0 and 1, theta is between 0 pi over 2, phi is between 0 and pi over 2 as well. And what this actually helps us see is that it's going to create the following picture here, and I'll go and explain as I show it to you. We end up getting this. And you'll notice that this is actually simply just 1/8 of a sphere. It's actually the sphere in the first octant. So imagine just drawing an entire sphere and chopping out just 1 octant of the sphere. And if on further inspection, you can kind of see that this is true. So for example, rho, again, don't forget, rho is the distance from the origin to the point itself. Now the point is not only the surface of this eighth of a sphere, but it's also everything inside. So basically you'll notice that if I were to draw a line all the way from here to, let's say, this surface over here, that's obviously a distance of 1, right? And so rho has a distance of up to 1 and everything in between. So that should make sense. Also, notice that my angle of theta, don't forget, my angle of theta is always on the floor, just like back in your days of polar coordinates. And because it's on the floor, notice that my angle goes from an angle of 0, which is here, right? That's my angle of 0, the positive x direction, out to and up to, but not passing the angle of pi over 2. We all know, I hope, that this angle from here to here is an angle of pi over 2. And again, don't forget, it's everything in between as well. Finally, our angle of phi is also from 0 to pi over 2. And don't forget that what's phi defined as? Phi is defined as the angle from the positive z-axis to the point itself. So again, notice that I start off with the positive z-axis here. This is phi equals 0, all the way down to an angle of pi over 2. And so essentially the idea is that our potential, or excuse me, our region of integration consists of an angle of theta from 0 to pi over 2, an angle of phi of 0 to pi over 2, and then it only goes out to 1 here because we are restricted by our rho values. So obviously, just kind of for example, if I could change this up a little bit to give you some perspective, if I kept everything on here the same, but I changed rho to, let's say, 4, all the 1s to a 4. But obviously that's not the problem in this case, so I'm going to go ahead and go back to my 1s. And hopefully you kind of understand how we ended up with this eighth of a sphere. Now, one other thing I would like you to notice is that if you actually look at the original integrand, you'll see what I have here is I have rho square sine phi d rho d theta d phi. Well, from the previous slide, well, this is just simply dv. And furthermore, notice that there's nothing else besides this value here. There's nothing else besides dv here. In fact, I could honestly, if I were to go back to rectangular coordinates, I could replace this with 1 times dv. And as I'll explain later in class, anytime you take the triple integral of 1 dv, we should already know this, then what is that going to equal to? Well, I'll show you here. Don't forget, anytime you're taking a triple integral of dv, where there's no other factor that's an integrand in terms of other variables, then you are essentially just getting the volume of this figure itself. So in this particular case, after we're done with this problem, the answer that we're going to get out of this problem here will just simply be equal to the volume of this eighth of a sphere. Let's go ahead and see if that's true. So again, like I said before, integrating this is not a problem. This is something I could have given to you a few sections ago, and you would have been able to integrate this without a problem at all. In fact, there's a few things I want to point out. Number one, notice that you can actually integrate this however you wish. Notice that I have a product here, rho squared times sine phi, of two expressions that one is explicitly rho, the other one's explicitly phi, and then there's no factor of anything that's explicitly theta. The point is, if you want to, you can actually go ahead and divvy this thing up into a product of three integrals, three single integrals, and integrate it that way as well. However you wish, really doesn't matter to me. Let's go and start by integrating this with respect to rho. Obviously, the antiderivative of rho squared is just power rule, so we're going to end up getting 1/3 rho cubed, integrating that from 0 to 1. We can kind of ignore this sine phi for now. Obviously, that's just going to give us 1/3. So we get 1/3 out of it. Obviously, this is pretty cake now, like a cakewalk here. The antiderivative of d theta, because there's no function in terms of theta here, is just going to be theta from 0 to pi over 2, which is obviously just going to give us pi over 2. And then finally, the antiderivative of sine phi is negative cosine phi from 0 to pi over 2. Okay, well, that's going to give us one time, or negative 1, times pi over 6 is just pi over 6. And let's see if that makes sense. If you recall, I told you in the previous slide that the volume is being found here. That we're actually literally looking for the volume of that eighth of a sphere here. Well, if we recall, the volume of a sphere is equal to 4/3 pi r cubed. The volume of a sphere is 4/3 pi r cubed. We know this from a basic geometry class. And if we simply replace r with 1, because obviously our radius in this case is 1, we end up with 4/3 pi, would be the volume of the entire sphere. Now, if you go ahead and take this volume here and just simply multiply it by 1/8, because we're just simply dealing with 1/8 of the sphere, you'll see we actually do get pi over 6 after you reduce all this. So it checks out. Now again, let's try this one more time. Let's go ahead and sketch the region of integration. And then we'll go ahead and integrate this. Once again, notice that I was actually not given any sort of function of rho, theta, phi. Notice that, again, strictly here I have dv. That's all they gave us in this case. So once again, whatever this problem may be, we're going to sketch out our region of integration, which is indicated by these three integrals. And once that's sketched out, the answer is ultimately going to be the volume. And again, if it's a very simple and basic shape, like the last one was a eighth of a sphere, you should be able to actually check it out and make sure it works geometrically, using some sort of simple formula. And we'll get to that in a moment. But let's start with our region of integration. So again, notice that our region of integration is given in spherical coordinates by the following. Notice here that theta is between 0 and 2 pi. Phi is between 0 and pi over 3. And so notice that my angles here, my theta and my phi, are both bound by constant numbers here. But rho, just like I mentioned before, sometimes your rho is not bound by constants. In fact, you'll notice the lower limit is 0, but my upper limit here is secant of phi. So that's definitely not a constant. But there are some ways to kind of determine if this is actually pretty easy to sketch. Now, you might think to yourself, how in the world is rho equals to secant phi easy to sketch? We'll just do some basic, rearranging of the factors here. You'll notice that my upper limit is rho equals secant of phi, which I hope you already can see that. It's obviously on the right-hand side of my inequality here. So I'm going to focus on that end of the inequality. That my upper limit is rho equals secant of phi. That should be easy to see. Well, if you simply multiply both sides by cosine of phi, so again, take this here. In fact, let me try to make this a little more clear. If I take this equation here and I simply multiply both sides by cosine of phi, what would that give me? If I simply multiply both sides by cosine of phi, I would end up with rho cosine phi equals 1. And as we all know, hopefully, by now anyway, we all should know that rho cosine phi is simply just equal to z. So simply replace rho cosine phi with z, and we end up with the equation of z equals 1, which is just simply a plane with a height of 1. So you might think, okay, well, that's fine. That's easy to graph a plane of z equals 1. But what about these other angles here? Well, just by showing you a picture, I think you can see what happens in this case. So I'm going to go ahead and just show you what this means. So basically, I'll get back to z equals 1 in a second. Let's first talk about theta is from 0 to 2 pi. What that basically means is that, again, the angle starts at 0, which is a positive x-axis, here. And theta is essentially allowed to rotate all the way around and back to the original positive x direction. That's what that means for theta. And then for phi, what that means is phi is allowed to start from the positive z-axis right here, okay? And you can have an angle of 0 all the way out to an angle of pi over 3 and everything in between. And combine that with the fact that I can rotate all the way around the positive z-axis, I end up getting this cone. Now, this is a little bit different than what we did before. Now, recall, we actually have graphed a cone before. But our particular cone in previous examples would actually keep on going forever. And we would only draw a circle on the top of it to represent, so that way we can practically graph it or draw a sketch of it. In this particular case, because my upper limit is z equals 1, in this particular case, this particular problem does in fact have an upper limit where this cone is truly capped off by this circle on top. So this, whereas previously this thing had no cap, it had no limit at the top, in this particular case, the highest this cone can go is a height of 1. So what you see is what you get here in this particular case. Now, before I continue on to the next slide, please maybe go back and try to see if this makes sense to you. Please try to compare these limits here, these integrals right here on the first part of the problem here. Makes sense for this particular picture, which is a cone capped off at a height of z equals 1. Now, integrating this thing is not going to be a problem. Integrating this thing is going to be quite simple. It's going to basically, again, like I said, I could probably present this triple integral to you in a previous section, and you'd probably be able to figure it out numerically and computationally. But understanding how to draw the picture using the definition of spherical coordinates is key. So let's go ahead and integrate this thing. Now, this is a little bit different. Yes, we are going to integrate with respect to rho first. Okay, we are going to integrate with respect to rho first, and that's going to be a very easy antiderivative. But this particular case, because my first limit of integration is from 0 to something in terms of phi, you can't separate these this time. You actually have to keep all this together. You could separate out theta, but you can't separate rho and phi. Rho and phi go together because the limits of integration here have a phi in it. So the antiderivative of rho squared is super easy. That's just 1/3 rho cubed. But notice again, my limits of integration are from 0 to something in terms of phi. So simply plugging this in, I'm going to get secant cubed phi. And again, you can ignore the 0 in this case, like we've noticed in the times past. And I just went ahead and decided to just clean it up a little bit. You can pause the video here and see how I got from here to here. All I simply did was put secant phi into the denominator, creating it to become cosine cubed phi. And then at this point, what I'd recommend you do is two things. One, again, notice that the differential of theta is next, which means it corresponds to this integration here. And notice that I am integrating something that is not explicitly in terms of theta. So that means I can just go ahead and take this out of the equation. I think we all know the antiderivative of d theta is theta. From 0 to 2 pi is just simply 2 pi. So if we take a look at this next step here, this 2 pi right here simply came from this step like immediately. I didn't have to do any work at all. I went right to it. And I haven't even integrated the phi yet. In fact, what I did here was I just took this expression here and made it into tangent phi secant squared phi, which to me is a little bit simpler of an integration. You can do that, or you can use substitution from your basic Calculus 1 class. Either way, you should still end up with 2 pi over 3 times 1/2 tangent squared phi from 0 to pi over 3. And again, after you do some simple computation, you end up with just simply pi. Now, I highly recommend, again, don't forget, anytime I do these problems, I do tend to skip a step here and there. I'm willing to show you the intermediate steps if you need me to. Please send me an email timestamping the place of where you have your question. But I still would highly recommend that you try to fill in the gaps. In fact, I highly recommend that maybe in a day or two, come back to this problem and try to do this from scratch by yourself from beginning to end without looking at my solution. Now, this one is truly where you are actually going from start to finish. You're starting from a rectangular coordinate base and you want to convert to spherical. Now, on your next exam, where this is going to occur, this will be in a few weeks. This particular problem, you'll notice that it says in the title, use spherical coordinates, but chances are on an exam, I wouldn't ask you to use spherical coordinates. I would let you do whatever you wanted to. But the clue or the key is that whenever you are bounded in a region of integration where they talk about spheres being the region of integration, typically you're going to use spherical coordinates. Now, you are more than welcome to try to integrate this thing using rectangular coordinates, and you would end up with the same answer. But is it going to be incredibly difficult? Is it going to be easier? Who knows? Once again, in many cases, if you are able to convert this to spherical, and after you do some algebraic simplification, it tends to become an easier problem to deal with. So in this particular case, why don't we go ahead and just start swapping things out here. You already know all your relationships. You know what x equals to, you know what y equals to, you know what z equals to. You even know this part. This part's going to be really easy right here. Obviously, x squared plus y squared plus z squared is going to become rho squared. We know that for sure. So that's going to be nice. And we end up getting this right here. So it should make sense that x is rho sine phi cosine theta. That's what became of this in front of the e. And then it's e to the rho to the fourth power. Well, it's rho to the fourth because here I have rho squared and it's being squared again. That's how I got rho to the fourth. And once again, please do not forget, dv must be replaced by all of this, just like before. Okay? So the replacements should not be a problem for us. That should be the easy part. The hard part really is determining these limits here of these integrals. But if you read carefully, it's really not so bad. First of all, let's take a look at this 1 to 2 for my rho values. Notice it's between the spheres x squared plus y squared plus z squared equals 1. That is a sphere of radius 1. This is a sphere of radius 1. This here is a sphere of obviously radius 2. So if my region of integration, E, is between these two spheres, obviously rho will be between 1 and 2, the radii of those spheres. And as you've seen before, we actually had a problem with this earlier. Whenever you see this, whenever you see phi is 0 to pi over 2 and theta is 0 to pi over 2, then that explicitly is dealing with the first octant. That's your clue that you're dealing with the first octant. So hopefully that kind of broke it down for you in a way that was understandable. So here I would like you to pause the video. I'm going to go ahead and erase all this stuff. And as you pause the video, see if that makes sense, the conversion from rectangular to spherical. Okay, now that we are ready to integrate this, the integration looks harder. The expression looks larger and more intimidating. But upon further inspection, you'll notice a few things. Every single factor of this integrand, you'll notice, is here. I have a factor of rho here. I have a factor that is explicitly rho here. I have a factor that is explicitly rho here. And none of these factors have rho kind of baked into the cake. It's all explicitly rho. Also, notice I have sine of phi here. I have sine of phi here. Again, both are factors that are explicitly phi. And finally, I have a factor of cosine here of theta that is explicitly theta. What does that mean? Well, let's go back a few sections ago when I talked about this. Whenever you have an integrand that is made up of a bunch of factors that are explicitly based on their own individual and respective variables, you actually can split this thing up. So notice how I actually rewrite this triple integral into a product of 3 integrals, where my first integral is explicitly theta, second integral explicitly phi, third integral explicitly rho. This is a beautiful scenario because when this happens, this is just essentially calculus 1 times 3. And obviously this is a very easy situation for just about anybody in our class. You simply integrate each one individually, clean it up, and the answer I got was 1 over 16 pi times the quantity e to the 16th minus e. Now again, after you do it, your answer might be a little bit different looking algebraically speaking, but if your answer is equivalent numerically, then I have no problem with your answer. Okay, to finish off this lesson, let's try yet another one. In this particular case, this one is actually kind of tough to understand, but what I'm going to go ahead and do is I'm just going to go ahead and give you the triple integral that I want you to see. Let's start with the easy part first. We all know that x squared plus y squared plus z squared is rho squared. So obviously taking the square root of that is just simply going to give me rho. So notice how here my integrand becomes rho. Okay? So that's the first easy part. The second easy part, again, remember that dv here must be replaced by rho square sine phi d rho d phi d theta. So that's the second easy part. So far, this integrand I don't think should be a problem for anybody at this point. The issue just might be, once again, the limits of integration. But once I draw the picture for this, you're probably going to see that it's actually not that bad. Let's go ahead and draw the picture. Now again, it's bounded below by the cone, and we should have experience with this because we did a cone very similar to this earlier in the class, where we had a cone that the angle was phi equals pi over 4. So this is going to be the same kind of idea. Since pi over 6 is less than pi over 2, this will be a cone that opens upward starting at the origin. So let's go ahead and draw one like that. So I'm going to try my best to draw one, so bear with me here. And it's bounded above by a sphere of essentially radius 2. That's what this is here. So kind of a crude drawing, but actually not too bad. So once I draw this here, I'm going to go ahead and show you what the limits of integration look like. So let's go ahead and take a look at these limits of integration. So let's start with the easy one. The easy one would be theta. So notice for both cases, for both the cone and the sphere, essentially you're taking some sort of angle and you're being allowed to rotate completely around 360 degrees completely around. So that kind of hopefully makes sense to you why the outermost differential with the outermost integral goes from 0 to 2 pi. That I'm hoping is the easy one. Okay. And also the cone should be fairly easy because if you look at the cone, use a different color here. So the cone here, it's obviously going to be, the cone itself is going to be the pi over 6 part of it. So the 0, what that means is it's everything inside the cone as well. So for everything from the positive z-axis out to the cone itself. So for that next portion, you'll notice that, again, this angle here, it's everything from 0 to the cone itself, and then again all the way around 360 degrees. That'd be for phi. Now rho, when I integrate with respect to rho, let's do again a different color. When we do rho, when we integrate with respect to rho, that's from 0 to 2. That's because this is bounded above by the sphere of radius 2. Now my sphere is probably not to scale, obviously. It's probably actually much more flattened than this. But the point is that the distance from the origin to the sphere itself, let's say that hits the sphere at that spot, that's no more than a distance of 2. And even if I go from the origin to this little edge over here, this origin from this little edge over here, it's no more than a distance of 2 no matter how you slice it. So it's a distance from 0 right at the origin all the way up to 2. So now that we see the picture along with the limits, it hopefully makes sense to you now. And I would highly advise at any time in this class, try to sketch a picture whenever possible, because that's going to help you understand much more clearly the limits and hopefully cause you to set up the integration properly on a more consistent basis. Because as I've said before, once the integration is set up, chances are the triple integral is not actually going to be that hard to compute. Now, as I've mentioned before, remember that this here, this p here, not p, excuse me, I'm sorry, this row here comes from the integrand from the square root of x squared plus y squared plus z squared. And because I have that extra value of rho, and on top of that I have my dv next to it, this is no longer a volume. This is now a hypervolume. So I have rho in addition to dv. So this is no longer a volume. This is a hypervolume. And we'll talk more about that momentarily. But this is essentially just the region of integration, and our actual answer that's going to come out of this will be a value that measures something even greater than this three-dimensional picture. Now, as far as the integration, this is a relatively easy situation here. So let's go ahead and integrate. So beautiful part about this, again, and you'll notice that this actually happens a lot in spherical integration, is that I have three explicit expressions here with explicit respective variables. So notice that I was able to split this up into three different single integrals, and the rest becomes a piece of cake. And then I didn't actually have room here to simplify this and make this nicer looking, but you can actually simplify this if you wish, or leave it as is.